Hi students, this is Mr. Eckert. We're going to go through target E5, which says that you should be able to describe the Hardy-Weinberg principle. It's actually a mathematical equation. And apply mathematical reasoning to explain gene frequency in a population of living things. So here's Hardy and Weinberg. They came up with this idea. They said in the absence of factors that alter them, the frequencies of gametes, the frequencies of genotypes, the frequencies of phenotypes, in a population are going to remain constant generation after generation. That's kind of like a duh statement, right? In the absence of factors that alter them. So if there's no factors that change them, they're saying the frequencies of these three different things, gametes, genotypes, and phenotypes, are going to stay the same. They also went on to say, though, that if the original proportion of genotypes, so you got to remember what a genotype is. Remember, that's how we symbolize alleles with letters. The original proportion of genotypes in a population is going to stay constant if all the following are met. The population size has to be large. There has to be random mating occurring within the population. Can't be any mutations. No genes are introduced or lost. So how could genes be introduced? Well, maybe by immigration. Organisms are coming in from another population. Or lost. Well, they could be lost through emigration, individuals are leaving, or they could die, right? And no selection occurs. So that means all the genotypes can survive and reproduce equally well. So they said in a large population that's mating at random, and in the absence of other forces that would change those proportions of the alleles, the process of sexual reproduction alone will not change these proportions. So they were able to come up with these two mathematical equations. These are the Hardy-Weinberg equations that you're going to use to solve different problems. So the first one at the top is the equation that you use when you want to figure out the frequency of the alleles. P stands for the frequency of the dominant allele in the population. So in this example, it would be big B, which maybe stands for the color purple. Q is the frequency of the recessive allele in the population. So in this example, that might be little b, and that stands for white. Notice that P plus Q always equal 1, and that should make sense. Remember that the frequency is just another term, we could say the ratio, or the percentage of the dominant allele in the population plus the percentage of the recessive allele is of course going to equal 1, right? They're going to, if they're percentages, they're going to add up to 100%. If they're frequencies, they're going to equal 1. Now, from this Punnett square, they were able to derive this equation here. Look what it says. P squared plus 2pq plus q squared equals 1. P squared is the frequency of the homozygous dominant individuals, and that should make sense to you. If we said that P is the frequency of the dominant allele, P squared is P times P. That's 2 dominant alleles. And who has 2 dominant alleles? Well, homozygous dominant individuals. Q squared, remember Q was the frequency of the recessive allele, so Q squared must represent then the frequency of the homozygous recessive individuals. And 2pq, well, that's somebody who has 1 dominant and 1 recessive allele. So, oh yeah, that's the frequency of the heterozygous individuals. So one thing that you will have to remember is that you're using this equation down here when you're calculating the frequency of individuals. Again, individuals have at least 2 alleles. So all of these in the factors in the equation have, here's 2 dominant, here's 2 recessive, here's 1 of each. So this is individuals. Whereas up here, those are by themselves. It's just 1 of each. So this is what the equation you use to determine the frequency of just the alleles themselves. Now, if you look over here at this Punnett square, you can see how they derive this. So when you do a cross between 2 heterozygous individuals, you get 1 homozygous dominant, that's the P squared. You get 1 homozygous recessive, that's the Q squared. And you get 2 heterozygous individuals. That's why they have 2 PQ. So add up all those frequencies, and of course you're going to get 1. If we change these to percentages, then of course it's going to add up to 100%. Alright, so now how do we use this to solve a problem? So here's an example. 1 in every 1,700 U.S. Caucasian newborns are born with a disease called cystic fibrosis. That's a real statistic. Cystic fibrosis is a recessive disease, so we're going to let big C represent normal, and that's dominant over little c, which represents cystic fibrosis. So when we start these problems, we almost always start by looking at the homozygous recessive individuals. And that's what it's saying here when counting the phenotypes, what they look like in a population. Why is the homozygous recessives the most significant or the most important? And that's what it's saying here, that 1 out of the 1700, this 1 is the one with cystic fibrosis. Those are little c, little c. So why do we start there? Well, if you think about the other 1699, those are made up of homozygous dominant and homozygous dominant and heterozygous individuals. But we don't know out of those 1699 how many of those are homozygous dominant, because they're going to be normal, and how many of them are heterozygous. They're going to be normal too. But what we do know is that only 1 out of that 1700 is the recessive, homozygous recessive. So we're going to start with that. So what percent of that population have cystic fibrosis? Well, remember, those are individuals then. Those are individuals who have cystic fibrosis. So we're going to use Q squared, and that is equal to 1 out of the 1700. And when you divide that out on a calculator, it comes out to 0.00059. If we want to change that to a percentage, that of course would be 0.059. You multiply it by 100 or move the decimal over 2 times. So Q squared is 0.00059 on your calculator. If you took the square root of this number, you would then have Q. So, and that's exactly what we're going to do. So we're going to take the square root of 0.00059. When you do that, you get this number, 0.024. So that is Q. And remember, Q is the frequency of the recessive allele. Once we know Q, we can plug it into this equation to find P, because P plus Q equals 1. So P plus 0.024 must equal 1. So 1 minus 0.024 is going to equal P, and that's 0.976. Once we know the value for P and Q, we can plug those back into the other equation, P squared plus 2PQ plus Q squared, to find the genotypic frequencies of those individuals. So remember, the homozygous dominants, those are P squared. So if we plug in our value for P and square it, we get 0.953. And remember, the heterozygous individuals who are carriers of cystic fibrosis, in the equation it tells us we find those by multiplying 2 times P times Q. So we're plugging in what we just figured out for P and Q, multiply it by 2, and we get 0.0468. So that is our frequency for the heterozygous individuals. Now, if we wanted to find out exactly how many people were homozygous dominant or how many were heterozygous, we're going to take those frequencies, multiply them by the total, and for the homozygous dominants, that would be 0.953 times 1700. That's going to be equal to 1620 individuals. Obviously, we'd want to round that decimal to the nearest whole number because we're not going to count people in tenths of a person. So how many are the heterozygous? Well, remember that we figured out was 0.0468. That was the frequency. We multiply that by the total, we get 79.56. We'd obviously want to round that to 80 individuals. Okay? It says it's been found that a carrier is better able to survive diseases with severe diarrhea. What would happen to the frequency of the recessive allele, little c, if there was an epidemic of cholera or other type of diarrhea-producing disease? Would that allele for little c increase, or would it decrease? What do you think? Well, if the carriers are better able to survive diseases with severe diarrhea, then obviously those who aren't carriers are not going to survive. So you can see how like the homozygous dominants, would probably succumb. And so you can see over time that the allele frequency for little c would probably increase then. Here's another problem: albinism, or albinos. You know that albinos have no pigmentation in their skin or hair, so they have very light colored skin and white hair. In humans, it says the average frequency is about 1 in 20,000. So remember that 1 in 20,000 are those that have albinism. It's a recessive disorder. So the 1 divided by 20,000 gives us the Q squared. That's the frequency of those recessive individuals. So that works out to be 0.0005. So that's Q squared. We're going to take the square root of this number to find Q, and that gives us 0.007. That would be equal to Q. We plug that into the P plus Q equals 1 equation to find P. So 1 minus 0.007 is going to be equal to 0.993. That's P. Once we know P and Q, we can plug those into the P squared plus 2PQ plus Q squared equation to find the other genotypic frequencies. So P squared would be this number times itself, and that would be 0.986. Plugging in this for P and this for Q, and then multiplying it by 2 gives us 0.014. That's the frequency of the heterozygous individuals. Okay? So that's it for that target. Now that target is a math target, and again, the way you learn math is by doing practice problems. We'll be doing practice problems in class. I would imagine that at this point, just going through the PowerPoint, you should probably be a little bit confused. So I would encourage you to, there are practice problems that are in the help folder. There's practice problems in the assignment folder. We are going to do practice problems in class. But again, the way you're going to learn these is to do the problems and to ask questions when you have them. So I would encourage you to do that.